Hello, this is John Miyares, and in this lesson, we're going to look at how we can apply the various trigonometric ratio ideas we learned in previous sections to our newly defined angles from section 6.1. Now, if you haven't done so already, you will want to make sure you go through the section 6.2b video and slides to get a feel for how we're going to be handling special triangles because they do come into play in this section and you might get a little bit lost without looking at that material first. Associated with every angle theta drawn in standard position is another angle called the reference angle, usually drawn and labeled with lowercase alpha. The reference angle alpha will be an acute angle formed by the terminal side of the given angle and the closest x-axis. So let's try drawing a picture of this. Suppose our angle has its terminal side in quadrant 1. Generally, assuming we're dealing with an angle which measures between 0 and 360 degrees, or between 0 and 2 pi radians, then the reference angle and the acute angle are going to be pretty much the same thing. So if you have what looks like a 50-degree angle, the reference angle will also be 50 degrees. If you have an angle whose terminal side falls into quadrant 2, then the reference angle is measured back upward from the negative x-axis. So if what you have is a 130-degree angle for angle theta, then the reference angle alpha will be 180 degrees minus that angle measure, which for that would be 50 degrees in that case. If we go into quadrant 3, the angle theta might measure somewhere between 180 degrees and 270 degrees, but the reference angle alpha will be measured back to the nearest x-axis, which is the negative x-axis again. So you'll just be subtracting 180 degrees from that measure. So if angle theta were 210 degrees, angle alpha would be 30 degrees. Finally, in quadrant 4, your primary angle might look something between 270 degrees and 360 degrees, but the reference angle is going to be something measured from the positive x-axis downward. So if this was a 300-degree angle for angle theta, our reference angle alpha would be 60 degrees, or 360 minus the 300. Now, if we were measuring angles in the negative direction, or if we were going multiple revolutions around the circle before landing in a particular quadrant, we could still apply the same idea. The reference angle will always be the acute angle formed between the terminal side and the closest x-axis. Let's try a few examples. Determine the quadrants in which the terminal sides of the following angles lie in standard position, and what is the measure of reference angle alpha. Here's the first one, 127 degrees. We can see that 127 degrees is bigger than 90 degrees, but it's less than 180 degrees, so that places it in quadrant 2. So the reference angle will be 180 minus 127 because we want to know how many degrees we are away from the nearest x-axis, which will be the negative x-axis at 180 degrees. So 180 minus 127 will give you 53 degrees. Let's try another one, 212 degrees. This is bigger than 180 degrees, but less than 270 degrees. So it must lie in quadrant 3. As for the reference angle, we want to know how many degrees we are away from the negative x-axis again. So we'll subtract 212 minus 180 to get 32 degrees. Why don't you take a minute to try these two on your own? One angle is positive, but the next one is negative. The focus will still be the same in that we're interested in what quadrant it lies in. Then once we know what the quadrant is, we'll be able to determine the reference angle by seeing how far we are from the closest x-axis. So 300 degrees will lie in quadrant 4 because 300 is bigger than 270 but less than 360. Then the reference angle will be 60 degrees because we're 60 degrees away from the nearest x-axis. As for negative 30, we're measuring in the negative direction, so that will put our angle into quadrant 4. Meanwhile, the reference angle will actually be positive 30 degrees, believe it or not. You only have to rotate 30 degrees back from the positive x-axis into quadrant 4 to get to negative 30 degrees. So the reference angle will just be 30 degrees. Here's two more you should try on your own. The first one is another negative angle, while the second one is not only a negative angle, but its absolute value is more than 360 degrees. Go ahead and give this one a try. So negative 135 degrees falls into quadrant 3, and the reference angle is going to be 45 degrees because we're only 45 degrees away from the negative x-axis. With negative 420 degrees, you're going around the one full circle clockwise and then an extra 60 degrees, which will put you into quadrant 4. Then the reference angle is going to be 60 degrees because you need to go 60 degrees backward to get back to the nearest x-axis. Now that we've spent a lot of time redefining what it means to be an angle, we're going to redefine our trigonometric ratios based on this new definition of an angle. Let's set up the initial conditions here, and then we'll talk about it for a bit. Suppose that a point P with coordinates x, y is any point other than the vertex on the terminal side of any angle theta in standard position. So what I've got here is that situation. I've got this angle. I've got my initial side on the positive x-axis. I've got my terminal side going up here. The point P that they're talking about might be this point 6, 8 that is on the terminal side of the angle. Let R be the distance from the origin to point P. And again, it says the two rays are often referred to as the initial side and the terminal side of the angle. To redefine the 6 trigonometric functions, what we're going to say now is that the sine of angle theta will be the y coordinate over the radius. The cosine of angle theta will be the x coordinate over the radius. The tangent of angle theta will be the y coordinate over the x coordinate. The cotangent is going to be the reciprocal of the tangent, x over y. The secant is the reciprocal of the cosine, radius over x. And the cosecant is the reciprocal of the sine, radius over y. So now what I bet you're thinking is that you just spent all of this time making sure that you understood what SOHCAHTOA meant, how SOHCAHTOA was spelled, and now you're worried that you have to completely throw that out and start over, right? Actually, you don't. What I want to do is look at this diagram and show how what we've learned about the rules of SOHCAHTOA can be expanded to this situation. We have this graph that shows an angle in standard position. The initial side is on the positive x-axis, and the terminal side passes through the point 6, 8. What we're going to do is draw a vertical line segment connecting point P at 6, 8 down to the closest x-axis to construct what I call a reference triangle. The triangle, the one side here is this dash segment going from point P down to the x-axis. We have a second side here is going to be following along the initial side, and then the third side, of course, is our terminal side of the angle. Our reference angle and our actual angle are going to essentially be the same thing here because the angle theta lies in quadrant 1. Now let's look at these definitions of sine, cosine, and tangent again. Back in section 6.2, we defined sine as the opposite side over the hypotenuse, cosine as the adjacent side over the hypotenuse, and tangent as the opposite over the adjacent. Well, if I focus on this reference triangle, then the opposite side is going to be the dashed line, and its length is going to be whatever the y value is because I'm measuring that distance up from the x-axis. So the y coordinate is the same as the length of the opposite side, which is the same as just the y value. Similarly, the adjacent side to angle theta, the side that runs along the positive x-axis, is going to have a length equal to x. So we can think of this value x as being the adjacent side in our reference triangle with respect to angle theta. Now, the other component of this was to get the hypotenuse, which we're now calling r, the radius of revolution in this angle. And in order to compute its length, we're going to have to use the Pythagorean theorem just like before. So for this triangle, we're going to have 6 squared plus 8 squared equals, well, 36 plus 64, which becomes 100. The square root of 100 is going to be 10. Now we have all three sides, x, y, and r. So we can evaluate the 6 trig functions, but because of how we've drawn this triangle, we can apply the rules of SOHCAHTOA. So the sine of angle theta, y over r, is going to be the same as the opposite over the hypotenuse in this reference triangle, will just be 8 over 10, which reduces to 4/5. The cosine, x over r, is adjacent over hypotenuse, becomes 6 over 10, or 3/5. The tangent is going to be the opposite side over the adjacent side, which in our reference triangle is y over x. That will become 8 over 6, or 4/3. The cotangent will be the reciprocal of the tangent, x over y, adjacent over opposite, to give you 6 over 8, or 3/4. The secant is the reciprocal of the cosine, so it is r over x, hypotenuse over adjacent, which will give you 10 over 6, or 5/3. Finally, the cosecant of angle theta is the reciprocal of the sine function, hypotenuse over opposite, r over y, which becomes 10 over 8, or 5/4. What I'm hoping you see here is that due to how we constructed this reference triangle by dropping a perpendicular from our given point on the terminal side of the angle back to the closest x-axis, the values of the 6 trig functions here that we're saying now are going to be using x, y, and r will still seem to follow the rules of SOHCAHTOA, because we'll see that the y value is the opposite side, the x value is the adjacent side, and the r value is the hypotenuse. And this works great, so long as the angles are in quadrant 1. Now, when we're working outside of quadrant 1, the concept is the same, but x and y could be positive or negative based on what quadrant the terminal side lies in. Possibly the x and y value could be 0 if the terminal side falls on either the x-axis or the y-axis. So what does that mean for us here? Suppose what I have is an angle in standard position like this one that passes through the point -2, -3. In order to deal with the sine, cosine, and tangent of this one, we will want to create a reference triangle and work with the reference angle, the one that we're measuring off the nearest x-axis, to apply the ratios to. So the first thing we'll do is drop a perpendicular back to the nearest x-axis, which is what I've done here. Although the angle itself may measure all the way around from the positive x-axis into quadrant 3, the reference angle will just be the acute angle between the terminal side of the angle and the closest x-axis. Once I have this reference triangle in place and have identified my reference angle, I'll mark the different sides of the triangle. Side y is the side opposite the angle. Side x is going to be the adjacent side to the reference angle, and side r is going to be the hypotenuse. Now, the r value will always be positive and can never be 0 because that would be an angle that never leaves the origin, so you really couldn't measure anything. Also, I'm mentioning this now, but we'll look more closely at it later. If x or y equals 0, that can cause some problems with how we'll compute some of the trigonometric functions because we could end up with some zeros in the denominator of our fraction. If I try to take hypotenuse over opposite and my opposite side has length 0, that could be problematic. Calculating the trigonometric ratios of angle theta that are not acute are going to be based on these reference triangles constructed by drawing a perpendicular segment from any point xy on the terminal side of the angle to the closest x-axis. Once the reference triangle is drawn and the reference angle alpha is determined, the standard SOHCAHTOA approach can be used to evaluate the 6 trigonometric ratios. However, the opposite and adjacent sides should be treated as directed distances, meaning we could label the side lengths as negative. So clarifying, what it means is that although the side opposite the reference angle, in this case, might have a length of 3, we're going to label it as having a length of -3 because the y value on the point on the terminal side of this angle is negative, or the y is heading in the negative direction. Similarly, the adjacent side x is going to be labeled with a length of -2 because we're going in the negative direction along the x-axis. So let's say our problem involved this very graph and we were asked to evaluate the 6 trigonometric functions associated with angle theta where the terminal side of the angle passes through the point -2, -3. We've already established our reference triangle and our reference angle alpha here in this diagram. We're saying our opposite side y has a directed length of -3 and the adjacent side x has a directed or signed, S-I-G-N, signed distance of -2. To find r, we need to use the Pythagorean theorem. X squared plus y squared will equal r squared. Substituting in what we know, we will have -2 squared plus -3 squared equals r squared, which expands to 4 plus 9 equals r squared. So r squared equals 13, which when we take the square root of both sides gives us normally r equals plus or minus the square root of 13. Now, r, we said, was always going to be positive no matter where we were on the graph, because that value r is going to represent the radius of a circle that is revolving around starting at the positive x-axis and going all the way around to the terminal side of the angle. Now we can evaluate the six trig functions here, assuming we have an opposite side of -3, an adjacent side of -2, and a hypotenuse of the square root of 13. The sine ratio is going to be the opposite over the hypotenuse. Y over r becomes -3 over the square root of 13, which we can rationalize as -3 square roots of 13 over 13. The cosine ratio is going to be the adjacent over the hypotenuse, x over r, which becomes -2 over the square root of 13, which again will rationalize as -2 square roots of 13 over 13. The tangent becomes the opposite over the adjacent, where y over x reduces to -3 over -2. The negatives will cancel, leaving you with 3/2. The other trigonometric functions are going to be reciprocals of these. The cotangent is the reciprocal of the tangent, the secant will be the reciprocal of the cosine, and the cosecant will be the reciprocal of the sine. Now notice when I'm taking the reciprocals in the last two, I'm actually working with the sine and cosine form that haven't been rationalized yet. In other words, I'm taking the reciprocal of -2 over the square root of 13 to get the square root of 13 over -2. This becomes easiest to work with because then we don't need to worry about re-rationalizing that denominator again. Now let's look at another example. Suppose you're told that the cosine of theta equals 3/4 and the terminal side of theta lies in quadrant 4. We want to determine the values of the six trigonometric functions of theta. Let's try drawing a picture of this situation. We have an angle in quadrant 4 whose cosine is 3/4, which means that x, the adjacent side, will have length 3 and the hypotenuse must have length 4. So I'm just going to eyeball it here and say it looks something like this. We can draw a perpendicular segment back to the x-axis as shown here. Then we can label the different parts of our reference triangle. The adjacent side is 3 and the hypotenuse is 4. This is what will help us create the idea of having an angle whose cosine is 3/4. Adjacent over hypotenuse, x over r, is 3/4. The opposite side is y, which is unknown for the moment. Angle theta is this big angle wrapped all the way around, and the reference angle alpha is this small one going back to the positive x-axis. To get the length of y, we're going to use the Pythagorean theorem, where I can substitute in my knowns x equals 3 and r equals 4 to use that information to solve for the unknown value y. Squaring these out and moving the constants to the other side will leave us with 9 plus y squared equals 16, or y squared equals 7, giving y equals plus or minus the square root of 7. For this example, since our terminal side lies in quadrant 4, then the y value of any coordinate in quadrant 4 is going to be negative. So the value I'm going to label in here for side y will be negative square root of 7. Now, realistically, again, the length is not going to be negative, but if we label as negative, then we apply the rules of SOHCAHTOA to the reference triangle and our reference angle alpha, we will be able to compute the correct trigonometric ratios here. So here are the six trigonometric ratios we're looking to evaluate. The sine of the angle y over r is going to become the negative square root of 7 over 4. The cosine of the angle theta which we're using alpha as a reference angle and creating SOHCAHTOA in order to do it, looking at x over r adjacent over hypotenuse is 3/4, which of course was given to us. The tangent will be the opposite over the adjacent, y over x, which is the negative square root of 7 over 3. The other three trig functions I'm not going to really spend any time on because they're just going to be the reciprocals of the three primary trig functions. At most, you may need to rationalize some denominators, but if you can get the three primary trigonometric functions, then the three secondary ones are only going to be that much easier to get, provided you remember which one is the reciprocal of which one. Remember, c goes with s, so cosine is the reciprocal of secant, and sine is the reciprocal of cosecant. This one is a little different. Suppose that the terminal side of angle theta in standard position is given by 2x plus 5y equals 0 in quadrant 2. Find the sine of theta, cosine of theta, and tangent of theta. And we have a hint that we're supposed to sketch this line. 2x plus 5y equals 0 is a straight line. If I rearrange it, what you're going to see is it has a line with a slope of negative 2/5, and it will pass through the origin. It turns into y equals negative 2/5 x. But we're only interested in the part of this line that lies in quadrant 2. So we're going to cut off the part of the line that continues into quadrant 4. And we'll get our angle in standard position to look something like this. Now, with all the other problems we've done so far, we've had a point on the line that could be easily identified. We can get that here, but we'll have to think about it some more. Since the slope of the line is negative 2/5, we can go up from the origin 2 units and back 5 units to get to the point negative 5, 2. From here, we'll drop a perpendicular back to the closest x-axis, and then we can identify the reference triangle and the angle in question. Remember, the actual angle theta we're interested in is this big one starting at the positive x-axis and wrapping its way into quadrant 2, whereas the reference angle will be this acute angle measured upward from the closest x-axis back to the terminal side of the angle. Now let's label some side lengths. The opposite side, or the y, is going to be 2, and the adjacent side, or the x value, is going to be negative 5 because we are heading in the negative direction along the x-axis in order to get there. The value of r is still a bit of a mystery here, but we can still solve for it using the Pythagorean theorem. Substituting in what we know for x and y, we'll get negative 5 squared plus 2 squared equals r squared, which expands out to 25 plus 4 equals r squared, or r squared equals 29. Taking the square root of both sides, you're going to get r equals the square root of 29. And we know we don't need to worry about the negative square root because r in these problems will always be positive. So let's label that on our triangle here as r equals the square root of 29. We'll look at our trig ratios and we'll come up with the following again. We have sine, cosine, tangent. We have SOHCAHTOA that we can apply here in place of the y over r, x over r, and y over x. The sine of angle theta is going to be opposite side 2 over hypotenuse square root of 29, which will rationalize as 2 times the square root of 29 over 29. The cosine is x over r, adjacent over hypotenuse, which will become negative 5 square roots of 29 over 29. The tangent will be negative 2/5, which happens to be the slope of the line. Coincidence? Maybe. Maybe not. Then the other three trig ratios are just going to again be the reciprocals of the first three. One of the common mistakes that people make in problems like these is in making sure that the signs, the SIGN signs associated with the six ratios are going to be correct. But this is something that we can always go back and double check for reasonableness. Based on the quadrant where the terminal side of the angle lies, you should always be able to tell which of the six trigonometric ratios are going to be positive or negative. From there, if you can determine the measure of the reference angle, you can redefine the problem you're working with in terms of the reference angle. So in quadrant 1, you have positive x and y values. So your opposite, adjacent, and hypotenuse are all going to come out to be positive numbers, which makes any trig ratio computed for angles in quadrant 1 come out positive. X, y, and r are all positive. Any way I set up a ratio with those three values will always come out positive. In quadrant 2, your x values are negative and your y values are positive, and of course your r values are going to be positive, which means that in this case, the only ones that are going to come out positive will be the sine, y over r, and the cosecant, r over y. All of the other four trig ratios will have negative signs attached to them because they all involve the calculation with side x, the adjacent side, which will be negative. In quadrant 3, both the x and y are negative, but the hypotenuse r is positive, which will make the tangent and cotangent come out positive because you're dividing a negative by a negative, which will cause the negatives to cancel, making the net result positive. The other four trigonometric ratios will come out negative because they all involve side r along with one of the negative length sides, x or y. Finally, in quadrant 4, you have a positive x and a negative y, which will make the cosine come out positive as x over r, adjacent over hypotenuse. And its secant, the reciprocal of the cosine, hypotenuse over adjacent, r over x. The other four trigonometric ratios will come out negative because they will all have to use side y, which is negative. So now let's try to see if we can find a quicker way to come up with the pattern. This sketch shows just the primary trig functions, sine, cosine, and tangent, because let's be honest, a lot of the time, that's what we're going to be working with. In quadrant 1, all of the trig functions come out positive. Then it's just the sine function in quadrant 2, the tangent function in quadrant 3, and the cosine in quadrant 4. If we focus on the first letters of those words as we go around the quadrants, A, S, T, C, for all, sine, tangent, and cosine, if we can remember that pattern, we can do our sign checks on the trigonometric ratios. So how do we remember this pattern of A, S, T, C? Well, a lot of people come up with their own sayings for them, such as amazingly smart trig class, or all students take calculus, or all skiers take chances, or all smokers try cigars, or all stoners try cocaine, or, well, you get the idea. Pick one that works for you and make it stick. Let's try a few examples together. Determine the quadrant where the terminal side of theta lies if you're told that the cosine of theta is negative and the sine of theta is positive. Well, the cosine is positive in quadrants 1 and 4, which makes it negative in quadrants 2 and 3. Similarly, the sine function is positive in quadrants 1 and 2. So combining those ideas together is what's going to give us that the angle we're interested in is quadrant 2. That is the quadrant where the sine function will be positive and the cosine function will be negative at the same time. Let's try another one. How about where the cosecant and cotangent are both negative? Well, the cosecant is the reciprocal of the sine. So wherever the sine, S-I-N-E, sine, is negative, then the cosecant will be negative there as well. And that will be in either quadrant 3 or quadrant 4. The cotangent will follow the behavior of the tangent. The tangent is positive in quadrants 1 and 3, and it will be negative in quadrants 2 and 4. So the cotangent will also be negative in quadrants 2 and 4. As we take those together, that leaves us quadrant 4 as the place where both the cosecant and the cotangent are going to be negative. Now we're going to combine the ideas that were presented in section 6.2b on special triangles with our ideas on reference triangles that we've just covered here in section 6.3. Suppose you are asked to evaluate various trigonometric ratios or trigonometric functions without a calculator, but you know that the reference triangle is going to be one of the special triangles we looked at in section 6.2b, either a 30-60-90 triangle or a 45-45-90 triangle. To do this, we should first try to draw a picture of the angle in question in standard position, then construct the appropriate reference triangle and determine the measure of the reference angle. We want to label the sides of the reference triangle based on the ratios of the side lengths for these known special triangles. But if you don't remember what they all are, you might be able to use the Pythagorean theorem in order to derive them. The leg lengths could be positive or negative depending upon what quadrant the terminal side of the angle lies in. The hypotenuse, or the radius, will always be positive. So here's our first example. Find the value of the sine, the cosine, and the tangent of 300 degrees without a calculator. Here is a sketch of that 300-degree angle, and we can see the reference angle will be 60 degrees. Dropping our perpendicular back to the x-axis, we can label the three sides of the triangle as we know them to be. The short side, across from the 30-degree angle, would have a measure of 1. The hypotenuse will have a length of 2, and the long leg will be labeled as having the length negative square root of 3 because we're measuring y in the negative direction because we're in quadrant 4. Focusing only on the three primary trig ratios right now, we can see that we'll have the sine of theta become negative root 3 over 2. The cosine of theta will be positive 1/2, and the tangent of theta will be the negative square root of 3 over 1. This one has the same idea. We want to find the sine, cosine, and tangent of 135 degrees without a calculator. So we'll start out as before by drawing out the angle. The terminal side will lie in quadrant 3, but I'm going to draw in what would be the entire circle all the way around so you can get a feel for why I'm using the term radius to describe what will be the hypotenuse of our reference triangle. One point that is clearly going to be on this angle is the point -1, -1. So we'll label that point here. And then we'll drop a perpendicular. So our angle theta will measure negative 135 degrees. But the reference angle measured from the nearest x-axis is only going to be 45 degrees. Now let's label our side lengths. Given that we're passing through the point -1, -1, we'll have the adjacent side x be -1, and the opposite side will also be -1. The hypotenuse will be the square root of 2, which we can get either from looking at the Pythagorean theorem, 1 squared plus 1 squared equals 2, or remembering how we're supposed to label this special triangle, 1 times 1 by square root of 2. The sine, cosine, and tangent can be read right off the reference triangle here. The sine will be negative 1 over the square root of 2, which simplifies as the negative square root of 2 over 2. The cosine will have the same value, negative square root of 2 over 2, based on the relationship of the sides in this 45, 45, 90-degree triangle, while the tangent will be reduced negative 1 over negative 1, which becomes just 1. Now, by the time you get to calculus, you will be expected to be able to compute various trigonometric functions of angles whose reference angles are tied to either 30, 60, 90 or 45, 45, 90-degree triangles. We're eventually going to practice these in the Mad Minute quizzes, and it will be critical that you be able to memorize these special triangles and know which quadrants will generate positive or negative trig ratios. However, there are some strategies that you can use to help you get a better understanding of these special triangles that will make things go faster. First, you need to know these triangles inside out and backwards, the 30, 60, 90 and the 45, 45, 90. Either memorize the side length pattern or try to remember how to derive them yourself. The 45, 45, 90, remember, is an isosceles right triangle, while the 30, 60, 90 is an equilateral triangle that's been sliced in half. We then want to combine those triangles with our understanding of the ASTC pattern that will help us decide whether a trigonometric function should be positive or negative based solely on where the terminal side lies. So here's a taste of what's coming. Rewrite each of the following problems in terms of an acute reference angle and a positive or negative sign. Then determine the exact values of the following trig ratios using what we know from the quadrant where the terminal side lies and the reference triangles. So I've got three problems I'm dealing with here: the sine of negative 60 degrees, the cosine of 225 degrees, and the tangent of 150 degrees. We want to first figure out what quadrant each of these angles lies in, then figure out what the reference angle should be. Then we must decide, based on the quadrant and which trig ratio we're working with, whether the value associated will be negative or positive. Then we're going to rewrite the expression and evaluate it based on our reference triangles above. So, negative 60 degrees lies in quadrant 4. Negative 60 degrees is 60 degrees below the x-axis in quadrant 4, so it will have a reference angle of 60 degrees. Finally, the sine function is going to be negative in quadrant 4. So what we're going to say is that the sine of negative 60 degrees is the same as the negative sine of 60 degrees. Negative coming from the fact that we're in quadrant 4, 60 coming from the reference angle. Looking at our reference triangles above, opposite over hypotenuse, the sine of 60 degrees is going to be root 3 over 2, so this expression will simplify as negative square root of 3 over 2. Let's try the same idea with the cosine of 225 degrees. 225 degrees will fall in quadrant 3. And the reference angle will be 45 degrees. Cosine in quadrant 3 is negative. Cosine is positive in quadrants 1 and 4. It will be negative in quadrants 2 and 3. So what we're going to say is that the cosine of 225 degrees is equal to the negative cosine of 45 degrees, which will be, when we look back at our reference triangle, the negative square root of 2 over 2. Why don't you take a minute to try the last one on your own? All right, 150 degrees lies in quadrant 2. 150 degrees is only 30 degrees away from the negative x-axis, so our reference angle will be 30 degrees. Tangent is positive in quadrants 1 and 3, so it will be negative in quadrant 2. So what I'm going to look to do is rewrite the tangent of 150 degrees as the negative tangent of 30 degrees. Negative because it's in quadrant 2, 30 degrees because that's the reference angle. Then I'm going to look at the reference triangle up above. From the perspective of the 30-degree angle, tangent opposite over adjacent is going to be 1 over the square root of 3. So this will result, after I rationalize, as negative square root of 3 over 3. All right, so those weren't so bad. So let's try a few harder ones. These examples are asking you to do the same exact thing, except all of these angles have a measure whose absolute value is greater than 360 degrees. So finding the quadrant they lie in will take a little bit of work. Additionally, the ASTC pattern that we talked about, all skiers take chances, all sine, tangent, cosine, that we use to determine the sine, SIGN sine for the trig ratios, only applies to sine, tangent, and cosine, not the secondary ones. So we're going to have to think about how these secondary trigonometric ratios behave relative to the primary trigonometric ratios they are the reciprocals of. What I'll give as a hint is that the secant will behave the same as the cosine, the cosecant will behave like the sine, and the cotangent will have the same sign patterns as the tangent, based on the fact that they're all reciprocals of each other. Perhaps we should pause the video for a minute to let you try these on your own first. All right, secant of 480 degrees. 480 degrees is going to be coterminal with 120 degrees, which lies in quadrant 2. The reference angle is going to be 60 degrees because as we get closer to the negative x-axis, we're only 60 degrees away from 540 degrees. Secant behaves like cosine. Cosine is negative in quadrant 2, therefore the secant will also be negative in quadrant 2. So now I'm going to take the fact that this is negative and the reference angle is 60 to rewrite the secant of 480 degrees as the negative secant of 60 degrees. Finally, we're going to look at our reference triangle, look at the 60-degree angle. We know the secant will be the reciprocal of the cosine. Cosine is adjacent over hypotenuse, therefore secant is hypotenuse over adjacent. With the sign being negative, our final answer will be negative 2 over 1. Now let's look at the cosecant of negative 600 degrees. As we unwind this problem, 600 degrees, or rather negative 600 degrees, is going to be coterminal with negative 240 degrees or positive 120 degrees, which again lies back in quadrant 2. And since it's coterminal with 480 and 120, it will have the same reference angle, 60 degrees. The cosecant is the reciprocal of the sine, and the sine is positive in quadrant 2. So our result here will also be positive. So rewriting this, I'm going to say the cosecant of negative 600 degrees is going to equal the cosecant of 60 degrees, positive. And then when I look at my reference triangle, the cosecant is the reciprocal of the sine. Sine would be root 3 over 2, so cosecant would be 2 over root 3, or rationalizing 2 root 3 over 3. Last one, cotangent 945 degrees. If we unwind that angle, go back a couple of revolutions, realize it's gone more than 2.5 rotations around the circle, 945 degrees is going to end up in quadrant 3. The reference angle is going to be 45 degrees. The nearest x-axis will be the negative x-axis, which would have been at 900 degrees. Cotangent behaves like the tangent, so in quadrant 3, tangent is positive, therefore cotangent will be positive. So simplifying matters, the cotangent of 945 degrees will be the same as the cotangent of 45 degrees. Looking at our 45, 45, 90 triangle, adjacent over opposite for the cotangent gives us 1 over 1, which will just be 1. All right, again, a lot of material was presented in this last section, but I'm hoping that you are beginning to see how everything is interconnected and it really isn't all that painful to work through. Here are the problem challenge problems for section 6.3. Please take your time to go through them, and if you have any questions, you know what to do. Don't be afraid to ask questions. Don't think that what you have is a silly question that isn't worth asking. The only silly questions are the ones that are not asked. Thanks for watching, and we'll see you all soon.